A catchment is an area of the Earth's surface that collects surface runoff and delivers the flow to its lowest point, the outlet or mouth. Surface runoff occurs as a progression of the following forms: overland flow, rill flow, gully flow, stream flow, and river flow. A catchment can be as little as less than 1 hectare and as large as several million square kilometers. The Amazon basin, the largest in the world, is about 7 million square kilometers, accounting for about 1/6 of the world's fresh water. In small catchments or watersheds, runoff is primarily controlled by overland flow processes. Overland flow is the two-dimensional flow on plains. Overland flow is governed primarily by flow convection with very little diffusion. In large catchments or river basins, runoff is primarily controlled by channel storage processes. Channel storage is the one-dimensional process of runoff diffusion, that is, flow attenuation, while the flow travels through the river channels. In mid-sized catchments, depending on size and prevailing slope, runoff is controlled by both overland flow and channel storage. The hydrologic characteristics of catchments are described in terms of the following properties: drainage area, catchment shape, catchment relief, linear measures, drainage density, drainage patterns. Drainage area determines the potential runoff volume, provided the storm covers the entire area. The larger the catchment, the less likely it is that a storm will cover the entire area. The catchment divide follows the peaks and saddles of the topography. The collection of peaks and saddles determines the physical location of the catchment divide. Because of subsurface flow, the topographic divide may not coincide with the hydrologic divide. In the absence of the detailed groundwater evaluation, the topographic divide is usually taken as the hydrologic divide. Runoff originates at high points at or close to the topographic divide and moves toward lower elevations in a direction generally perpendicular to the terrain's contour lines. Several formulas have been proposed to relate peak flow to catchment area. A basic formula is in which Q sub P is peak flow, A is catchment area, and C and M are empirical constants. The U.S. Geological Survey uses this formula in the regional regression equations for estimating flood peaks at ungauged sites. For example, the 100-year flood peak for the state of California's northeast region is Robert Horton was a distinguished American engineer and scientist, considered by many to be the father of modern hydrology. Horton described the outline of a normal catchment as a pear-shaped ovoid. Large catchments, however, can vary widely in shape. A form ratio based on catchment area is defined as follows. In which K sub F is a dimensionless form ratio. A is the catchment area, and L is the catchment length, measured along the longest watercourse. The compactness ratio is based on the catchment perimeter. An equivalent circle of area equal to that of the catchment is defined. The perimeter of this equivalent circle is calculated. The compactness ratio is the ratio of the catchment's perimeter to that of the equivalent circle. In which K sub C is the compactness ratio, P sub C is the catchment perimeter, and A sub C is the catchment area. A high form ratio, or a compactness ratio close to 1, describes a catchment having a fast and peaked catchment response. Catchment response refers to the relative concentration and timing of runoff. A faster response leads to higher peak flows. Conversely, a slower response leads to lower peak flows. Other factors such as relief, vegetative cover, and drainage density are usually more important than shape in determining catchment response. Maximum catchment relief is the elevation difference between the highest point on the catchment divide and the lowest point at the catchment outlet. The principal watercourse is usually the longest watercourse and the one conveying the flow to the outlet. Relief ratio is the ratio between maximum catchment relief and the longest horizontal distance measured along the principal watercourse. The relief ratio is a measure of the intensity of erosional processes, or geodynamics. Catchment relief is quantitatively described with a hypsometric curve. A hypsometric curve is a dimensionless plot portraying the variation of surface area with elevation. To develop a hypsometric curve, several elevations are selected within the range of possible elevations, and partial areas above these elevations are calculated. Elevations relative to the minimum elevation are expressed in percent of the maximum elevation difference. Partial areas are expressed in percent of total catchment area. Percent elevations are plotted versus percent partial areas to obtain the hypsometric curve. The longitudinal profile of a stream or river is a plot of streambed elevation versus horizontal distance. In the absence of geologic controls, longitudinal profiles are usually concave when viewed from above. A convex streambed profile is an indication of the presence of geologic controls, that is, rock outcroppings. Channel gradients are directly related to bottom friction and inversely related to flow depth. Typically, bottom friction increases and flow depth decreases in the upstream direction. Conversely, friction decreases and flow depth increases in the downstream direction. Channel gradients vary widely, from steeper than 0.1 in typical mountain streams to as mild as 0.000006 in some estuarial rivers. The S1 slope is the channel gradient obtained directly from the maximum and minimum elevations and the associated distance between them. The S2 slope is the constant slope that makes the shaded area A1 above it equal to the shaded area A2 below it. An expedient way to calculate the S2 slope is to equate the total area below it to the total area below the longitudinal profile, that is, A1 equal to A2. The equivalent slope S3 takes into account the basin response time. The channel is divided into n subreaches, each of length L sub I, and a slope S sub I is calculated for each subreach. The time of travel T through each subreach is equal to its length L over its velocity V. That is, it is directly proportional to its length and inversely proportional to the square root of its slope. The sum of times of travel for all subreaches leads to the equivalent slope S3. The U.S. Geological Survey's regional regression equations compute channel slope between 2 points located at 10% and 85% of the channel, measured in the upstream direction. The USDA Natural Resources Conservation Service determines average surface slope by overlaying a square grid pattern over a topographic map of the watershed. The maximum slope at each intersection is evaluated and the average of all values determined. The catchment length, or hydraulic length, is the length measured along the principal water course. The length to catchment centroid is the length measured along the principal water course, from the catchment outlet to a point located closest to the catchment centroid. Stream order is essential to the hierarchical description of streams. Overland flow is a hypothetical zero order. A first-order stream receives overland flow. Two first-order streams combine to form a second-order stream. The catchment's stream order is the order of the main stream at its mouth. The drainage density of a catchment is the ratio of total stream length to catchment area. Total stream length is the sum of all individual stream lengths. Overland flow length L sub O is the mid-distance between stream channels. Drainage density D is approximated by the following relation. Thus, mean overland flow length L sub O can be estimated as 1/2 of the reciprocal of drainage density. Basin drainage patterns vary widely. Various types of drainage patterns are shown here. These drainage patterns reflect the local geology and geomorphology, and secondarily, the influence of soils and vegetation. Drainage patterns are related to hydrologic properties such as catchment response or annual water yield.